Hello, I'm Joe Buckley. I'd like to talk to you about the principles and applications of terahertz non-destructive testing. Bourne Whedon are responsible for the worldwide NDT market promotion of the TeraMetrics equipment, which is manufactured in Ann Arbor, Michigan. Terahertz radiation is in the part of the electromagnetic spectrum which lies between microwaves and the far infrared. This region has historically been difficult to investigate because the frequencies involved are too high for electronic methods and the wavelengths are too long for optical methods. It's therefore been known as the terahertz gap. It involves frequencies ranging from approximately 100 gigahertz up to 10 terahertz, which correspond to wavelengths in free space from 3 millimeters down to around 30 microns. Recently, there have been advances in combining optical and electronic methods, which have allowed for the generation and detection of signals in this range, with acceptably high signal-to-noise ratio and high data acquisition rates. Consequently, there has been a surge of interest and an investigation of the capabilities of terahertz radiation is underway. You see here the typical range of terahertz radiation. For NDT, we are normally talking about frequencies from around 100 gigahertz up to 1 or 2 terahertz, and this represents wavelengths comparable to those we are used to dealing with in ultrasound, giving us inspection resolutions that are useful for real-world problems. Terahertz radiation penetrates through most non-conductive materials and can reveal imperfections such as voids, cracks, and variations in density. A key advantage is that terahertz radiation is non-ionizing and involves no safety issues. Some examples of terahertz imaging applications include floor detection of sprayed-on foam insulation in applications such as the space program, detection of threat objects in airline baggage, we're all familiar now with terahertz scanners that we walk through, and measurement of complex multi-layer coatings. This is especially useful where other techniques such as ultrasound are ineffective due to the nature of these coatings, which may, for example, not transmit ultrasound very well. When terahertz waves pass through an interface between materials having different dielectric constants, some of the energy is reflected. We can measure the strength and timing of these reflections, and we can then calculate the thickness of the material layers and assess whether or not they are intimately bonded. We can thus detect voids and layer separations. You see here a typical A-scan presentation from the TeraMetrics equipment. You see a reflection in one phase at the top of the material and in the opposite phase at the lower side of the material. This is similar, although not identical, to the presentation we would expect with ultrasound. There are many applications of terahertz radiation and more are being developed. In industrial process control, it's used to measure the thickness of non-conductive materials. It can be used to correlate the strength of the reflections to area density, for example, in measuring the weight of paper. It can be used to detect delaminations between layers. In aerospace NDT, it's being used to measure coating thickness and to locate defects in high technology materials. There are also many research applications of terahertz radiation, such as spectroscopy, which we'll talk about a bit more later, various types of imaging, and it's also been used in a number of cultural heritage applications, for example, measuring multiple layers on paintings. The single point gauge is configured to allow the measurement of up to 3 layers simultaneously. Different recipes or programs can be selected to evaluate different products. The next video shows this being used for measurement of a 3-layer fuel tank. For NDT applications, we use a laser pulse of approximately 100 femtoseconds length. This generates useful amounts of electromagnetic energy from approximately 100 gigahertz up to around 3 terahertz. To detect the reflected or transmitted terahertz energy, we use a similar device which becomes conductive when hit with a laser pulse. In this case, the resultant current is the product of the laser on-off parameter and the energy of the incoming terahertz wave. By changing the delay between the transmit and receive laser pulses, we can measure a specific point on the waveform. By linearly changing this delay, we can produce an A-scan style digitization of the terahertz waveform. In the TeraMetrics equipment, this is done by rotating multifaceted mirror, which can produce a rapidly changing path length, thus scanning through a delay time range at a rate of several hundred times a second. For this to work, the optical pulse length, or in other words, the sample time of the sensor, has to be significantly less than the period of the terahertz energy. This shows a typical spectrum from a laser pulse. We can see there is energy extending up to around 2 terahertz. Note that we will also see absorption lines on the Fourier transform of frequency. These correspond to water vapor in the air. These images show the TeraMetrics range of equipment and show typical configuration used. We see here a scanning system for laboratory use, a system with separate transmit and receive transducers for through transmission testing, particularly for spectroscopy, a process control setup with a fixed sensor head and a terahertz control unit. For handheld quality applications, we see a single point gauge and a line scan gauge. Every system requires a terahertz control unit. There are currently 4 versions of this available, the main difference being the rotating mirror assembly fitted. There are 2 versions capable of 100 Hz PRF, allowing either a 320 picosecond or 700 picosecond long A-scan. This allows work on thicker materials. There are also 2 1 kHz PRF units available in 80 or 160 picosecond A-scan length. This gives higher resolution but limits the thickness of the material you can test. Into these units we can plug a single point gauge, a line scan gauge which only works with the 1 kHz PRF units, or some kind of online sensor head for process control. There is also an explosion-proof version of the online sensor head available for use in hazardous environments, for example when measuring paint coatings online. There are some key limitations with the terahertz system. One of the obvious ones is that they can only work on non-conductive materials. Even carbon fiber is too conductive to see past the first couple of plies. The other important limitation of terahertz measurements is limited thickness. Because we generate the time delay for the received signal using a combination of an adjustable optical delay and a rotating mirror, the A-scan length is limited. Typically, with the 1 kHz PRF 160 picosecond path length version, the maximum reflection range is around 17 millimeters in a typical plastic. So allowing for some positioning error when we need to measure both the front and the rear face simultaneously, the maximum practical thickness is around 13 millimeters. We can, of course, shift the 0 point as long as not seeing the front face and the rear face simultaneously is okay, but this will normally require very stable positioning to make any measurements. The 100 Hz PRF unit can be specified with up to 700 picoseconds A-scan length. This corresponds to around 75 millimeters in the plastic. In this slide, we can see a variety of images produced using the TeraMetrics equipment. Images can be carried out in either through transmission or reflection mode. You'll note particularly the image of a credit card where the numbering is clearly visible when viewed through an envelope. Perhaps this is why modern credit cards no longer have embossed lettering. This video shows a live B scan produced by the equipment. The terahertz sensor is scanned back and forth across the parts, allowing real-time images to be created. These are some of the many applications of the terahertz equipment in imaging and measuring industrial products. In this system, the sensor head scans back and forth across the product, measuring its thickness. This is used in conjunction with real-time control of the roller pressure to ensure that the product is even and of the correct weight. The TeraMetrics equipment has been used extensively in evaluation of high-technology coatings on modern aircraft. The explosion-proof version of the online sensor head was developed for mounting on a spray gun. As each layer is applied, the thickness can be measured in real time, allowing the coatings to be accurately built up to the desired thickness. The step check, which became the line scan gauge, was developed for measuring the accuracy of butt joints to ensure they were level and that the gap between plates was correct. The single point gauge is configured to allow the measurement of up to 3 layers simultaneously. Different recipes or programs can be selected to evaluate different products. The next video shows this being used for measurement of a 3-layer fuel tank.
T-Gauge SPG, or single point gauge, is a handheld terahertz measurement tool for the determination of layer thickness. First developed for the Air Force to measure specialty aircraft coatings, the SPG can also be used for fuel tanks, multi-layered plastics, rubber, paint coatings, coated pipe, and any time that a spot check of thickness is required. Coatings can be measured on metal or composite substrates. Based on the robust T-Gauge industrial measurement platform, the SPG sensor head provides a simple and versatile alternative to ultrasound. Able to perform measurements that ultrasound cannot, it also does not require a coupling medium and is able to travel through air. The terahertz pulse reflects from each product interface, and the time between these reflections is a measure of the layer thickness. The specifics of the product, such as how many layers it has and the layer properties, are defined in a measurement recipe and can be selected from the touchscreen on the handheld tool. The SPG can measure layer thickness to 10 micron precision. To access hard-to-reach areas, the SPG is reconfigurable to allow the use of 1-inch or 3-inch lenses and can switch between straight or right-angled positions. The contact cone assists the user in maintaining the proper focal distance from the product being measured, but can be replaced with standoff legs if necessary. There are 2 measurement modes. The triggered mode performs a measurement as soon as a valid reading is obtained after the trigger is pulled. If desired, a tone can be set to indicate when the measurement starts and ends. A second mode, continuous, allows the operator to view the measurement over a period of time. This allows scanning of an area to see how the thickness changes with position. A continuous tone, related to the strength of the signal return, can aid in maintaining proper alignment as the SPG is moved across the surface. The measurement starts when the trigger is pulled and is stopped when the trigger is released. Each result can be saved in a separate CSV text file on a USB storage device attached to the control unit. If there is a predefined sequential protocol for product measurements, all the results in the sequence can be automatically saved to a single text file. Either the triggered or continuous mode can be used when creating the file. The T-Gauge SPG is a versatile measurement tool to spot check the thickness of a coating, layer, or multi-layer product. Up to 3 layers or measurements can be displayed at one time, and the predetermined measurement definitions can be selected from a list stored in the SPG. Coupled with a cost-effective T-Gauge Terahertz control unit, the SPG is the latest in a series of compelling Terahertz products.
The handheld line scan gauge scans across a width of approximately 50 millimeters 4 times a second. It requires a 1 kHz PRF waveform acquisition terahertz control unit. The line scan gauge was originally developed for measurement of step and gap between body panels. It can also be used for detection of bond line defects underneath insulation and for a variety of defect detection applications in composite structures. Here we see the line scan gauge being used to investigate the internal integrity of plastic body panels. Internal defects here are not structural, but can result in blemishes on the finished vehicle. This is a much larger scale application of terahertz measurement. Here you see the equipment being used for internal imaging of the foam insulation on a space shuttle fuel tank. It's more recently been used on heat shield imaging, which is a similar application involving materials that are very difficult to penetrate with any other method. Radomes represent an excellent application for terahertz imaging since they are designed to be non-conductive and transparent to radio waves. Here we see terahertz imaging of a radome support bracket structure. Here, terahertz imaging is being used to check the integrity of a composite repair patch. An application where the properties of terahertz measurement are particularly useful is in evaluating water intrusion into a laminate panel. In this case, it would degrade the performance of the radar equipment as well as producing local heating. The terahertz equipment can be tuned for the water absorption lines and is thus extremely sensitive to discriminate this problem. When flat roofs are constructed, the underlying seal is a plastic sheeting which is heat bonded together. Defects in this bonding can result in water leaks, which are exceedingly difficult to locate and repair once the structure has been completed. Terahertz measurements are used after bonding to confirm the integrity of the joint and avoid later problems. This can reduce significantly the insurance costs. This shows the TeraMetrics T-Image platform, which is a C-scan device which can be used in either the through transmission or reflection mode. It is readily portable and can be mounted vertically or horizontally. It includes motion control electronics, which are connected to the TCU via a network cable. This image shows the effect of a spectroscopic examination, producing a picture based on the absorption line of methanol at just over 1 terahertz. We can readily distinguish between a bottle containing only air and a bottle containing methanol vapor. This video, produced by a TeraMetrics customer, shows a robotic system being used to take thickness measurements of a plastic bottle for statistical process control purposes. If you would like further information, have any questions, or would like to discuss a terahertz feasibility study, please contact us at the details shown.